but he wants to get the autocorrelation. So I'm going to do autocorrelation today, and then either the next lecture, probably the next lecture, talk about the spectral energy density of a system or of an actual function, because you know, autocorrelation, if you just receive a signal from the air and you're wondering if there's information there or not. Now basically, you know how it looks like noise. If you actually look at the time domain for most stuff, you can't tell. So if you capture enough data and sample it fast enough, you can do a fast Fourier transform and you can see spectral components. And whenever you see specific frequencies, that tells you there's information. It's much more than that, but that will give you all you need to know. The fact that that signal is not, you might say, naturally occurring. It's something man-made that you need to investigate. By the way, have you ever heard of this search for extraterrestrial intelligence SETI? Any of these projects? No. Do you know where Arecibo is? The big facility down there? No. You know where? Okay. Probably 40 years ago, 50 or something, there was a big interest in trying to figure out if there's intelligent life outside of Earth. Seems reasonable. Scientists need something to do. They're astrophysicists and astronomers. So anyway, and here's the real genesis of this. They captured a signal. It was supposedly from deep space, and it showed all the signatures of intelligent life. And basically it was a conversation, some kind of information was there. And it wasn't based on something naturally occurring from the universe. It's very easy to find. Everything we know of in the universe itself is wide sense stationary process. Even impulse functions like black holes, well, I shouldn't say black holes, but things that explode, these supernovas you've heard of, I think, right? Things like that have a very clear signature in the frequency band. So this is at least the story, you can look it up. That drove people to start listening in deep space for any radio signal that looked like it might have a promise of something created by an intelligence besides us. It's not easy to do this because everything we send out reflects back, remember that, even from the moon, even from other planets. So it's not as easy as you think, just to look in the, the darkest place in space and just keep listening. So anyway, the whole idea of information theory and more or less information being part of a signal came, that whole science, you might say, or the theory, the mathematical theory was sort of driven by a lot of this, but there's more to this. So in radar, another thing we do is we capture signals. I'm trying to give you some information about why it's important. So we send out signals and then we listen and we get signals back. And they can be signals that were created by the enemy or by somebody trying to spoof you, or they could be our signals, and there's a lot of things we do. But one thing we do, when we send a signal, we try to make it as unique as possible at the low frequency, and it's called baseband. And then we modulate it to a high frequency signal. Usually it's an amplitude modulated, but it can be phase modulated as well. And then we capture whatever comes back, and we get a data record of everything that we capture. And then we do something called correlation. And we can see, anytime the autocorrelation function peaks, we know that that's likely the total round trip time from a target. Y'all follow me on this? So we can figure out where targets are at a given azimuth and elevation. And we can do more than that. We can do autocorrelation functions in frequency and take the fast Fourier transform. And we can actually see spectral components where they may be transmitting over a narrow band trying to jam us. So there's more to this story in his PowerPoints, and I'll get to him today if I have time. He goes through an example of why it's important to think, or to at least appreciate the reason for it. So back to this problem, the age-old problem. And I'm going to talk about, now his book doesn't give a proof for it. He gives a hand-waving proof for what's going on. His board needs a little attention, and I may do that in a second. But anyway, so This is in section 6.1, 6.2, and in 6.3, but I'm just going to tell you this. What he has is a signal, and I can call it S of t. It doesn't matter what you call it. And it can have a value of A, or it can have a value of minus A. And he's going to show you this in the book. And what happens is that there's another piece of randomness to this, and this is called T0 would be this time. So he's going to say there's some random time T0 that becomes, actually that's not T0. This is going to be T0 right here. And I've got to make sure I draw it the way he did it. Tell you where it is on the power or on the PDFs, because I don't want to confuse you here. He's going to have this as T0, and the width of every one of these sections is going to be TA. So basically, what it says is from the time a transition occurs until the next possible transition, doesn't have to transition, and the average value of this binary signal is going to be 0, which means the number of positive or plus A's pulses is going to be the same as the number of minus A. Can y'all follow me on the reasoning behind this? But there is a randomness to it, so if this is T0 and the width of this is TA, this point right here would be T0 minus TA. I don't like some of the symbols he uses, but I'll live with them. Then there's another section TA, but there could be, so this is going to be T0, and that width, this would be T0 plus TA. And it would continue. Now remember, it doesn't have to be a transition. And then there's a couple other things he says about it. Did anybody read this section in there or look at it? Did you read it or just look? All right, now he doesn't say this explicitly. Well, he does say it explicitly, and mathematically he doesn't prove any of this, but he's saying over this period of time, there's statistical independence between everything that happens over this period of time and this period of time and this period of time. The reason that's important is this. If they are statistically independent, whatever happens after TA occurs, basically, if it's statistically independent, then the expected value of X of, and I'll call it T, times X of T plus anything greater than TA, and I can just say alpha TA is just going to be the expected value of X of T times the expected value of X of T plus alpha TA, and make sure alpha's magnitude is greater than 1. Y'all with me on this, class? So if you take any distance greater and the separation between the 2 points is greater than TA, it means whatever happened here has nothing to do with what's happening there. That's what it means. Well, if this is the case, then that's just the expected value of X times the expected value of X, because we're assuming wide sense stationary ergodic signals. Can y'all follow me? Basically, it means that whatever the expected value of the functions, and he calls it, I call it X, you can say S of T is X of T, it doesn't matter. Now that's important because if the expected value of this, the average value is 0, if the statistically speaking, the number of positive and negative transitions is the same, then this is 0. Y'all with me? Now that gives us the clue on how this autocorrelation is going to happen. So back to the autocorrelation function of tau. That is the expected value of X of T times X of T plus tau. Y'all with me? And if tau is greater than TA, it's 0. Y'all follow me on that? The reasoning behind it's critical. Because there's statistical independence and the average values of it. So it's going to be equal to 0 if tau's magnitude is greater or equal to TA. That's it. Now, when he talks about the expected value of this, if it's less than that, I like to get rid of, and I was alluding to this on Friday, get rid of T0. What you're doing is adding too much complexity. This problem isn't that hard. So if you look at it just from the point of view of first pulse, what I'm going to do is make it as simple as possible. I thought about the way to do this. If I just have this as A, and remember, the only thing I really care about is what's going on in this range. Y'all follow me? Because I could draw, I could keep drawing out the sequence, but anything out here, and I'm talking about doing autocorrelation, so I'm going to take 2 points in time. But anytime I get more than TA apart, it doesn't matter. Now I'm going to superimpose beneath this one, this pulse. This has a width TA, this is A. And remember, we're within the sample period of the trip. There's nothing transitioning over this time, I should say. This is assuming we're from T0 to T0 minus TA to T0. Y'all with me? You're in that range. Now right here, and this will be my X of T, and here's my X of T plus tau. And I'll make sure that tau right here is less than or equal to TA. So it looks like this. And remember, this would be TA. I got rid of that T0 for a reason. It doesn't do a thing. Here's this pulse. Height A. The width of this is TA. Since this is TA right here, this width here, you could say this is really going to be TA minus tau. And tau here, something like that. Y'all with me? I'm just drawing it. Actually, this would be the negative. It would be X of T minus tau. That's okay. Do y'all follow me on this? It would be a right shift. The right shift's always a minus value, but T minus something. Y'all with me? It won't matter. It's a symmetric thing. Now, the overlap area is right here. It's almost like a convolution kind of thing. Can you all see that, class? And what you have to do, the expected value of that times that is what we're looking for. Y'all with? Now, what is that? Well, this is maybe oversimplification. So it's the expected value of X of T times X of T plus tau. And if you think about that for a second, over this range, you have to always get the probability density of the thing occurred, right? And that would be, in this case, 1 over TA. Y'all give me that one, right? So it's going to be 1 over TA. And then you're going to have A times A, or A squared. And then it's going to be TA minus tau, right? Or if you look at this, I hope you can follow this. So it's this width right here would be TA minus tau, or it would be tau, wouldn't it, class? Let me see here. Wait a second. No, I take it back. This width would be messed up. I'm saying the pulse starts at tau. My bad. This would be tau right here. This would be tau plus TA. That would be the skew. I'm sorry about that. That's the way he's doing it. What I'm really trying to do is get that shift, because remember, if tau is 0, they have to overlap. Can y'all follow me on this, class? Tau is 0, they have to overlap, and then they shift. This is shifting that way, so this is going to be TA minus tau. And you might as well put a magnitude of tau here, because all autocorrelation functions are always symmetric and even, so you can put a magnitude of tau there. It will, our Rx of plus tau is Rx of minus tau. Come, everybody follow me on this, class? Now take a look at that. What is it gonna be? It's a squared, and then it's gonna be 1 minus magnitude of tau over Ta. And this would be for tau less than or equal to Ta greater than or equal to 0. Or in the magnitude too. So that will work, and that shows you with the autocorrelation. Yes?
Does the 1 over Ta come from the fact that it's uniform?
It's probability density. Basically what we have to do is, if we're doing this, we have to get a probability density of the next expected value. Now, because it's ergodic, we can do it in time, or if we had the joint density function, we could do it using, you know, the x1 of t, x2 of t. But what I'm doing is kind of a time average here. That's all I'm showing. Anyway, for this one, what it amounts to is the autocorrelation function. I'm going to put it here. I mentioned it last time, but this, remember, it's really critical to understand this. This only works if the probability of a minus transition or minus A is the same as the probability of plus A. So the average value is 0. What I'm about to show you will not work if you have 0 to A transitions. We're going to get to that one. It's real important to see this. So if you look at this right here, here's what it looks like for this function. And it's in this book. Rx of tau versus tau looks like this. And this would be Ta, and this is going to be minus Ta, and the peak value here is just A squared. And that's it. That's all it is. Now, if you think about that, that's a triangle function. We're going to make mention of something. Now, in Dr. Denny's notes, and I think in the book too, but I don't remember exactly, he says that the Fourier transform has to be strict positive. Do you remember this, anybody? If you have a Fourier transform of any kind of legitimate autocorrelation, it has to be strict positive. I'm mentioning it here. It's not in this section, but I want to make sure you write this down. So if you have this as an autocorrelation function, do you remember the triangle function of Fourier transforms? Let me give you a real quick primer on this, because it's going to come in handy in a second. And I'm just going to take you back to some real basic stuff for you, but I need to do this just to get your head on straight. So if we have delta t here, here's what we're going to do. This is going to be the type of function in the time domain and the type of function in the omega domain. And by the way, f of omega is going to be equal to the integral from minus infinity to infinity of x of t e to the minus j omega t dt. That's the standard I'm going to use. If you had it with f, all right, then you're going to have 1 over square root of 2 pi in front of this stuff. Do you remember using f instead of omega, everybody? F is 2 pi. I mean, omega is 2 pi f, and if you all had signals and systems, right? Did you use omega? All right, never mind. In communications, you're going to use f, and it's real simple. Omega is 2 pi. It's real simple. Anyway, this is called the forward transition, or we call it analysis because we're looking in the spectral domain for information about the signal. So that it's typically called analysis in most engineering applications. This is synthesis. If I want f of, I call it f of omega, it should be capital X of omega. If I wanted to synthesize a signal and I knew in the frequency domain what I wanted it to look like a filter or something, and I wanted the impulse response to that filter, then I'd get x of t would be equal to 1 over 2 pi integral from minus infinity to infinity of my x of omega times e to the plus j omega t the omega. These are the relationships, one from the other. You probably remember that, right? This is always analysis. We're analyzing a signal to see in the frequency domain where the information lies, what it looks like. And this is synthesizing a signal if we knew like the filter characteristics. If we knew h of omega, say an ideal filter, and we wanted to get an actual h of t, the impulse response, we'd use the bottom one. Back to this thing. If I have a delta function, what does it look like in a frequency domain? Please know this one. Please make sure you know this one if you don't. Yeah, think your index finger. It's just one. You can prove it real quick. Put a delta t in here. Only value of delta t that's not zero is delta t equals 0, right? Well, t equals 0, height is infinite, width is infinitesimal, area is 1, e to the 0, 1, it's 1. That's the way I think about it. Now, I'm going to keep going on this. That's delta t, if I have e to the minus at u of t, what happens over here? Guys,
1 over a.
it's going to be a plus j omega, right? Y'all remember that? I'm very curious. I mean, you got to use this stuff in comm and stuff like this continually. He's always going to be assuming, Dr. Tugnick will assume you remember this stuff. And I've known from the history of my teaching that some kids need a little push in the right direction. Remember, you've got to remember. You're really in trouble here. All right, now one comment here. If it is a true u of t, in other words, if a is 0, then there is an impulse that occurs here. Do you remember that? It's pi times delta of omega here. Now, the reason is because if you think about a transition that's super sharp in the frequency domain, think about the impulse up here. Delta t goes to 1. What is u of t actually? Well, it's not a delta function in a true sense, but it has a transition. The steepness is infinite. You follow me on this? And the way you do it, take a derivative of a delta function, what do you get? U of t. I mean, a derivative of u of t, you get a delta function, right? We can mess around with it all you want, but there is going to be a delta function right there that shows up because of that transition so sharp. Then there's another thing that happens for stuff like this, and I'm going to mention 1 or 2 things. So the pulse function I use is p tau of t. It is the same thing as rect of t over tau. Do you remember the rect function, pulse function? How many do? You need to know these. So what does it look like? Well, a pulse function just has a height of 1, if this is time, and the width of this is tau. So here it would be minus tau over 2. Here it would be tau over 2. That's what it looks like. Do you remember the transform of it? It's an important one. It's tau times the sinc of omega tau over 2. Kind of, sort of. Anybody remember? You got it? All right. A lot of times they don't use omega, they use 2 pi f, and you can see the 2's cancel. So you get pi f tau. That's used all the time. And that's a sinc function. By the way, do you know, how many know what a sinc function is? You don't? Really? Don't remember? Really important. I'm going to show you this. I'm going to put it up here because it's so important. There's 2 definitions that are used. Now, and I stated explicitly in every course which one we're going to use. In this one, we're going to use the sinc of x is equal to, this is a really fundamental definition, in my opinion, sine x over x. That's all it is. Now, if you look at that at x equals 0, it's undefined. You have sine is 0 is 0. When x is 0, it's 0. 0 divided by 0 is undefined. So you have to take a derivative of the top and bottom. Derivative of sine x would be cosine x, right? And derivative of x is 1. Well, cosine x, then you have to evaluate them both at 0, and you see it's 1. You all see that, class? And for this one, right here, it looks like this. A sinc function looks like this. They used to call this, and I think they still do, they call that an elevated cosine function. It looks like you take a cosine function and just dampen it as it goes down. That's all, it looks like a 1 over x times a cosine almost, if you look at it carefully. Follow me on this, class? But it's magnitude of x, cosine x over magnitude of x. Not quite, but it's close. Anyway, that's a sinc function. Now, when you take a look, remember, the pulse function or rect of width tau, it goes to a sinc function, it looks like that. The height would be tau. And if you look at this, that's the width of the pulse. So the thing I'm telling you is, the narrower the pulse, the steeper the height. And you can see in the limit, as the width goes to 0, that goes to infinity, it starts looking like an impulse function. The next one is the one I want to get at, that you kind of have to know, and that's called a triangle function. Well, don't have to know, but at least you should. And on the final exam, this is where you really get in trouble if you don't have an understanding of some of these basics. So if we have a triangle function of tau of t, how many remember the triangle function? I call it a triangle. You do? It's just a triangle. That's it. What it looks like is that without a squared. Think of that without a squared, put it 1. That's the triangle function. As a matter of fact, the mathematical statement for a triangle function is just this. But there's one caveat to this. It's going to be multiplied by a pulse function of the width, tau, all right? That way you can't have values greater than or less than tau. I mean greater than tau over 2 and less than minus tau over 2. And you're going to find out that will be important. So typically, this triangle function is really going to be 1 minus, and here it would be t, magnitude of t over tau, but it would be tau over 2. So it would be 2 magnitude of t divided by tau, and then it would be times a pulse function of t, just to keep everything within the range from minus tau over 2 to tau over 2. That's what a triangle function is. Anybody remember the Fourier transform of a triangle function? I'd be surprised. Do you? Or not? No? No. You're looking at me hard like I don't trust you. There is one. But this is the point. This is tau over 2 times the sinc squared of omega tau over 4. Now I bring that up for a reason. Remember how I said the autocorrelation functions, Fourier transform, is strictly positive? Do you remember reading that in the slides at all? Did I get it? You did good. It's important to know that. Now look at this. This is a triangle function. This function right here, if I take the Fourier transform of that, and believe it or not, I might as well just say this. If you take, it's called a spectral energy density function. So Sx of omega is the Fourier transform of Rx of tau. And this is called the spectral energy density function. Now, I have to say something. If you get something that's repetitive or has cosine components, something that never dies down to 0, then you wouldn't have a spectral energy density function. We'd have to do a, you might say, a limited, over one period, we take the Fourier transform of the autocorrelation, and what we get is, it would be over the longest period, we get something called the spectral power density. Remember, energy, anytime you have a pulse that's time limited, in other words, it doesn't go on forever, the Fourier, the actual energy in that signal is going to be finite. It's not going to be infinite. Anytime you have a finite duration pulse. But anytime you have something that's on for infinity, then you have an infinite amount of power, but you have a power density. You might say you have a power spectral density function. Okay, just keep that in mind. Anyway, this one, can you see that this function right here is strict positive because of the sinc squared, the nature of sinc squared? The sinc function isn't. But the sinc squared is, so it checks the box. This is the Fourier transform of this. It's strict positive. It checks the box. It's a legit autocorrelation. That's one way to do it. You can also see, if it was sinc squared, Follow me? It's got some, then you get this, you would have no negative peaks, there would be all positive values, and the Fourier transform would be strict positive. That's important, at least to appreciate. All right, now the next one I'm gonna do, I'm throwing a lot at you right here, but I wanted to just get you at least thinking about this, because we're gonna use this. If we have enough time, we're gonna use it a lot, but probably not a whole lot. Do you have any kind of laboratories where you do fast Fourier transforms of signals and get information at all? Nothing? It's helpful, because in the real world, kind of live in that domain for anything with radar communication and well, a lot of the analysis is done in frequency domain. Weren't all your circuits done in frequency domain, constant frequency? Like you assume a meganaut and then do everything at like 10 volts at 30 degrees, isn't it? It was assuming a constant frequency, right? But it's, I mean, it's low frequency, it's called AC analysis. But then you get variable frequency analysis. All right, next. After that, well, this is important. So we covered the one plus or minus a average value of the waveform is 0, right? Now here's one that occurs, and I'm just going to show you the spectral energy density, the autocorrelation is. We're going to have a signal. I'll call this x of t, but it's going to transition from a to 0 as the only possible values. So it can be a, or current transition is 0 here. Call that TA. Maybe it doesn't transition there, then it does here, and it keeps going. Y'all follow me? I'm just trying to show you something where you look at this. And this would be A. Now here's the important thing to know about the feature. You have to know the average value. So if I say that positive transitions occur, say the A is equated to 1, and 0 is equated to the 0, the digital logic. You have to know the ratio of the number of zeros to ones sent. If it's exactly 50-50, which they usually try to do, then we can easily figure out some information. But if, say, A was sent only 1/3 of the time and 0 was sent 2/3, statistically speaking, that would give us a different average value of x. That's why it's important. With me, class? All right. Now, for an autocorrelation function of this, there's something to see about it. One is, since the average, if we'll assume that each one of these occurs at 50% of the time. That's the one I think that is most appropriate to use. So if it occurs 50% of the time, the average value would just be what? 50% or 1/2 times A plus 1/2 times 0, or simply A over 2. Do y'all agree with that? Let me see this right. It's the average value, if you say A occurs 50% of the time and 0, same number as 0 and 1 sent. The average value is going to be A over 2. If the width is, if there's no difference in width, right? So my average value, or the expected value of just x of t, is A over 2. Now, if you look at that and think back to the one I did before, the autocorrelation function for this, I could do this and map it out, and I could basically take this waveform and skew it, like I did before, and just skew this thing to be tau, and this would be still TA here, and this has an area of A, and we could figure out, remember, we could figure out what that area is. Do y'all follow me? And we could go through it, but here's what happens because of this. Look at the autocorrelation of that function in the PDF that I posted where this is, because there's some tricky stuff here. I know it's Denny's slides. This is on page 227, figure 6-5. So I'm going to just talk about this. I think this. Remember, if when we think about autocorrelation, it's the expected value of x of t times x of t plus tau, right? Now, if there's no overlap, if you think about this, if all of a sudden tau is greater than ta, can you all see how this function would have no overlap of the pulse that's actually being shifted? You all follow me on this, class? Can you see it back there? If that's the case, or if I say for tau, magnitude of tau greater than ta, over here, the autocorrelation function of tau becomes the expected value of, and now we have two pulses that aren't in the same interval, or the expected value of x of t, then I can multiply, because they're statistically independent is the idea behind this, times the expected value of x of t plus tau. Well, for the pulse I'm showing here, where it goes from 0 to a, 50% of the time, the expected value of x right here is going to be a over 2. Do you agree with that? And if you take a look at that, the way he has it, yeah. If you take a look at this right now, for this one, I'm going to have the expected value of x of t, a over 2, times the expected value of a over 2. Basically because they're statistically independent, so there is no correlation coefficient between the first and second. And that means it's just a squared over 4, and that's true. And then, when you take a look at what it is, when they overlap exactly, I'm looking for that one. Let me try to show you this. So if they overlap exactly, it's this pulse multiplied by itself. Do y'all follow me? Well, it's still only, I have TA here. This actually should be TA right there. This should be TA. Or no, actually you can do it with TA here. But what it's going to end up being, if you take a look at that, the expected value technically it would be 1 over, you have to go over to here actually, TA to C, because statistically you need to get this variance. So 1 over 2 TA, and then it's going to be the integral from 0 to 2 TA of, here it's a squared, a times a, or a squared, and then, oh, I'm sorry, a squared, but it would be dt over from 0 to a. What I'm trying to do, I'm not capturing this very well. I'm trying to say because half the time it's 0, it's not minus a. Remember, the other one, it can be either a or minus a, right? So it doesn't matter if you're taking a times a or minus a times a, you get an a squared there. You follow me in this class? So the average value when it overlaps is a squared in that case. But because we have a possibility of 0, we have to at least include that possibility. So I'm saying if it's 50% of the time, I'll go from 0 to 2a. And on this one, I simply get a squared over 2 as the expected value of that, simply because the transitions can be 0 or a, not a or minus a, like the other one, because minus a is going to be a squared as well. So if that's the case for this one, that's the expected value, the RMS value, or the, sorry, not RMS value, the mean squared value, which is the autocorrelation of 0. And then you can see that Rx of tau will be equal to, and the way he does this is going to put it as, let's see, a squared, or what he does is actually draw it first. If this is Rx of tau versus tau, here it's a squared over 2, and that's really x squared bar. And then it'll come down, this would be TA, and then the average value of this thing becomes a squared over 4, and a squared over 4. Now, what it amounts to is the peak value is not a squared anymore, but a squared over 2, and the average value isn't 0, but a squared over 4. And I'm going to say this much. I think most systems that are digital are something that are non-return to 0, aren't they? Anybody doing digital in here? Stuff. Do you remember, you can, whenever you have 0 and 1s, binary systems, you can send signals with non-return to 0. Do you all remember this? Or not? Do you remember the terminal? You all had digital, didn't you? Didn't he go through the different types of signal? There's non-return to 0, there's 0, I mean the 0-1 system is where you start, right? Binary system. But the 1 can indicate like a plus A, the 0 a minus A, that's non-return to 0. If you have a 0, then the problem is with the 0 is you get an autocorrelation function that's got an RMS, basically an average value out here. And so it's always going to have a value. It is legitimate, that one. This is legitimate. But this would be the autocorrelation. I'm going to make 2 comments about this one. So far, the only thing we've done is say both of these systems, either system 50% of the time you're A, 50% you're minus A, or 50% A, 50% 0, both of those systems are common, you might say, in the way signaling is done, and the autocorrelation functions are known. But what we haven't done is covered something where the pulse itself is no longer going to be E, basically say it's A only one, basically a transition occurs only 1/10 of the time, and those things get trickier. I want to spend a whole lot of time on the possibilities, because you can imagine, you can have systems, boy, there's a whole lot of things. You can have random pulse widths. We did this when I did some of the pulse coding for my graduate student, myself did this, and we had pulse coded baseband signals. This is throwing a lot at you, but it's the low frequency signature that we're going to modulate and send. And we made them something so they would be completely uncorrelated. Everything in the past has nothing to do with the future, but we have to keep a data record. We have to know what we sent. So when we catch the reflected signal, we can do this autocorrelation, cross-correlation it's called, because it's a different signal. And we can see where targets are very accurately. and the Doppler velocity too. But there are a whole bunch of things that can happen at this point. What I'm going to do now, I'm just thinking out loud to myself that it's probably better that I do some examples and then go to the PowerPoints, because there's almost too many possibilities. I mean, what if the signal doesn't go binary? What if it's trinary? Or what happens when we get more variability, both width of the pulse, position, say it's a random pulse width, amplitude, all this stuff. You can also almost imagine how crazy it can get to try to figure out the autocorrelation. So I'm going to show you, I want to do some problems, then I'll go to the PDF. And I really, at this point, I'm struggling on how to make this, how to make sense out of some of this. Actually, why don't we do this? Why don't we do, let's see, an example first. I'm not even sure which one this is. Let's start with exercise 6.2.1. But what I want to do is do these things where you can see some of this stuff apply to problems. This is example 6-2.1, is it?
Yes.
And what page is that on?
215.
Okay.
It says, the speech waveform is sampled 4,000 times a second, and each sample is quantized into
Is it 4,000 or 41?
4,000. And each sample is quantized into 256 amplitude levels.
Okay, the number of levels, binary levels.
The resulting amplitude levels are represented by a binary voltage having values of plus or minus 5.
Okay. So this is non-return to zero. With me on this? A 1 is a plus 5, a 0 is a minus 5. Think of it that way, non-return to zero. Now if you look at this, the general autocorrelation function I gave you for this, generally, if you remember it, would be a squared, and then it's going to be times 1 minus magnitude of tau over Ta. And this would be true for tau magnitude less than or equal to Ta, and it would be 0 else. And I'm going to try to draw that real quick. You don't have to draw this, but I'll show you. This is tau this way. Everybody with me? Now here's the important thing. We have that frequency, right? But when we sample it, we have 2 to the 8th levels. That's 8 bits. You all follow me on this? So we have 8 bits. And that means as we sample the signal, think about that, this value of TA, really, every time we sample it, we're going to have 8 bits, either ones or zeros, that have to be sent. Does this make sense to everybody? We don't have 1 bit, we have 8 of those bits. So in fact, the value of TA there would be, instead of, it would be 1/8 the value, basically over the we sample once, 1/4000 we sample. But then we take that sample, we turn it into 8 bits that have to be sent. Each of those bits is going to be 1/8 the actual width. Y'all follow me on this, class? That's the thing you worry about, is the minimum possible bit width in the time domain. And I say width, but you know, in the time domain, the time domain spectrum, what is the actual frequency or the width in seconds that you would need to transmit 8 bits over TA seconds, or over 1/4000 seconds, whatever that is. So it means this, TA on this one would be equal to 1 over the sample frequency, which would be 4000 hertz, then the number of bits that have to be transmitted during that time. If you think it through, you'll see it. You sample, we have to create 8 bits. Those 8 bits can be ones or zeros. It's that many things happening over TA. And they can be ones or zero, but they're sent. That's the idea, they're sent. Now when we look at that, if we want Rx of tau, and this is only good for tau less than or equal to TA, so Rx of tau would be equal to A squared. What would A squared be for this one? I'm gonna let you figure that out.
25.
Y'all see it's 25? It's important you do. So it's 25. And then, next thing I have is 1 minus, and this is magnitude of tau over, what is it, 32,000? Sorry, it's 1 over 32,000, isn't it? Seconds, and that would mean that it's going to be 25, and it's going to be 1 minus 32,000 times magnitude of tau, and this is going to be for tau less than or equal to 1 over 32,000. And does he have something equating to that?
That's what he has.
But I'll warn you, here's the reason I'm doing this one. I messed with these things last night. Whenever you see TA, you think of a single frequency. It's got to be 1 over the sampling frequency. Yeah, if there was only a binary bit, a 1 or a 0 sent, that would be true. But there's 256 levels, which is 2 to the 8th, right? What if there's 512 levels? 2 to the 9th, correct? So then it wouldn't be 8, it would be 9. Y'all follow me? What if it's 1024, 2 to the 10th, right? 10 levels. It's always the number of binary bits that you would be sending. And that's critical. Now, if it was trinary, then it's different too, because now it would be what? 3 to the end. Y'all follow me on this, class? There's 3 possible states. So if you sent a -5, a 0, and a 5, usually we don't mess with stuff like that. That's well beyond anything we care about, because almost everything that I know of that's done today is digital signal processing. Binary should be a better word for it, signal processing. Digital, I mean, whenever they say it's quantized levels, well, you can have 16 quantized levels if you think about 16 sort of bits. You can have 16 possible levels that are associated with a signal transmission. It could be like plus 16 volts, plus 15, plus, you all with me on this? Instead of just +5, -5. But almost always it's 2, and there's a lot of reasons for it. Okay, that's that problem. Now, I want to go to the back of the book and do at least one more. Oh, this Now this one's irritating, and I gotta tell you something. I don't expect you to know every trigonometric identity. Most of these identities I'll give you if you need it, but you should at least be familiar with these things so you know you're looking for an identity. These are trig identities. I'm gonna go through this problem. This is gonna be 6-3.2, I believe, in the problems in the back. Into the chat. By the way, if you took the Fourier transform of that, that's a triangle function, y'all with me? You can get the Fourier transform of that and prove it's strict positive. I won't ask you to do that on the next quiz. And now the final, depending on how much we get done on Friday, I may ask, but I'll tell you straight up, some of them I would have to give you tables for because you're not that versed, unless it was, just a delta function. You haven't used those things that much. So this is 6-3.2, I believe.
Random process has sample functions of the form x of t equals y times cosine omega naught t plus theta.
So far, so good. It looks fine. Wrong. Here's where it gets complicated.
In which y, omega naught, and theta are statistically independent random variables.
So they're saying y, omega, and theta are statistically independent random variables. Got that? Now, y is interesting because it has a mean value of
3
and a standard deviation
of 3, yeah, it's
sorry,
variance is 9.
of 9. Okay, what about omega naught? As an
It's
average?
It just says
Uniform?
it's uniformly distributed from -6 to +6.
All right, so omega naught, here's the density function for it. F of omega naught goes from -6 to +6, and the height has to be 1/12. And what about theta?
Uniformly distributed from -pi to pi.
All right. Everybody was doing this? So he wants some information. What's the first thing he wants?
Is this process stationary
And
or organic?
all right, now here's something to prove this is a bit tricky, but I gotta tell you this. First, do any one of these mean values change with time or standard deviations? All right, it means it's stationary. Y'all with me? That's all it means. Ergodic is if the time domain average is equal to the average you'd get statistically speaking, and the answer is no. So it should say not ergodic. You're not going to be able to really appreciate this because the proof. Here's what I'd have to do. If you look at this, because they're statistically independent, the joint density function is going to be 0. Do you all follow me on this? It's going to be just the probability of density. The f of x, comma, f of xy is, you know how it's x comma y, and then you get something, right? That one is just f of x times f of y. And since we have 3, it would be f of y times f of omega times f of theta of theta. Y'all with me? Now, if you go through the statistical, if you take that and you do the average value of that, you're going to get 0. If you do it, if you do that in the probabilistic domain with the f of x, f of y, and f of z, you're going to get 0. But if you do it with the time domain averages, you don't, so it's not ergodic. And I believe he says not ergodic. Doesn't he say something like that?
It just says the process is stationary but not ergodic.
All right, stationary, nothing changes with time as far as the averages or mean, or standard deviations or averages. That's all you have to know. He didn't even prove it, I don't think, but it is not ergodic. And don't worry, I'm not gonna ask for that level of detail in any kind of a testing I do on you. But the next thing he asks for is,
Find the mean and mean square value of this
Alright.
process.
now when we want the expected value of this, that's the expected value, y, right? And then it's times the expected, this is the tougher one, of cosine of omega naught t plus theta. I'll get to this in a second. But y'all realize because these are statistically independent, if I have y times x, the expected value of that is just the expected value of y times the expected value of x, right? Well, I don't have x, I have this cosine waveform, but I can do some funny stuff. So the expected value of y is 3. So I've got the first part. That's from the definition. Now this is the expected value of, and this is a cosine A plus B identity. So it's going to be cosine of omega naught t times the cosine of theta minus sine of omega naught t times the sine of theta. Now first, do y'all agree with me so far? I'm just doing the expansion. Cosine A plus B is cosine A cosine B minus sine A sine B. And I think he has that in there, but I don't remember if he used that proof or not. Are you with me on this one, class? Trust me, this is one of the ways to do this. Okay, now you see how this is basically 3 times, now these two are statistically independent, theta and omega, right? So it'd be the expected value of cosine of omega naught t times the expected value of cosine of theta minus dot dot dot, and I'll explain why I'm putting it there. Now remember, omega and theta, right? Should do it this way, are statistically independent. If theta is from minus pi to pi, evenly distributed, what's the average value of a cosine function over a period from 0 to pi?
0.
It's 0. Do y'all know that? Omega t here is from minus 6 to 6. It's evenly distributed, right? That's going to be 0 as well. Are you with me on this? You can prove it if you want. It's 0. So this goes away. And by the same token, the average value of the sine of theta is 0. Well, 0 times anything. You don't even have to do the sine of omega naught t. Y'all follow me? It's 0. So that goes away. That means this is 0. Y'all see this, class? Does he have that for that one, the expected value? Okay, check that box. Great. Now we want the mean squared value, is that it? Okay, for the mean squared value, what are we gonna do? Well, if I square this thing, this one's a pain. It's a lot of terms, but I'll try to do it quickly. So if I take a look at this, the expected value of x squared is the expected value of y squared, right? Times the expected value of, actually this one is maybe not that big of a pain. What's coming up will be, of cosine of omega naught t plus theta squared. I'm just putting down, I'll try to hustle through this. Y'all with me? Now, what is this going to be? Expected value of y squared. Well, y squared bar would be equal to, what would it be? It would be, pardon me, it would be what? Sigma y squared plus y bar squared. Do you agree with that? So what is that? That's, isn't that 12? Correct, class? First, sorry, did I mess up? Sorry. I'm sorry, 18. So it's going to be 3 squared plus 9, so it's 18. my bad, 18. So come over here. This part's easy, this is 9, right? Times, now that's, this, I'm gonna show you the one. Whenever I see a cosine squared, what is cosine of A squared? Isn't that 1/2 plus 1/2 cosine of 2A? Do you remember that identity? Anybody? How many do? One. Well, you'll use this continually in Dr. Tugnay's class and a couple of the other classes. You know how you get this real quick? I want to just give you a secret. Anytime you get into trouble, you're wondering about what identity to use Euler's definition, cosine or sine. Y'all with me? So what is Euler's definition of cosine? It's e to the ja plus e to the minus ja over 2. Y'all follow me? Now square it, you'll see it. Take that and square it. You get 1, take a look at this, 1/4 comes out in front. Then you get e to the j2a there, right? Take the last term, plus e to the minus j, and just look at this, it's going to be 2a, right? And then you're going to get the cross terms plus 2. Can y'all follow me? I'm showing you a trick. I use this all the time. Either for, do y'all know the identities? Sine of theta and cosine theta is e to the j theta plus e to the minus j theta over 2. Sine theta is e to the j theta minus e to the minus j theta over 2j, right? Those things will save you so much. And I'm speaking from experience, because I had to deal with this. Can you all see how the 2, and I mean 1/4 times 2 is going to be 1/2? And then you get what? This, e to the j2a plus e to the minus j2a, that's 2 cosine of 2a, right? So that's going to be plus 1/2 cosine of 2a. That has saved me so many times when I was in your shoes. And you're just getting into the fun part of your curriculum. You get random, you're going to get communications, and then you get your higher level courses. Okay, so that in mind, I said for one reason. Here, I'm going to have what? And the answer in the book on this one is wrong. 1/2 here plus 1/2 cosine of, and now it's going to be double that, so it's going to be 2 omega naught t plus 2 theta. Do you agree with that? But I need the expected value of that, so I better do this. So I have 9 times the expected value of this whole thing, right? Do you agree with that?
I think it's 18 times that expected value.
I'm sorry, you're right. You're absolutely right. It's going to be y squared, my bad. It's 18 from over there. But what do you notice about this? Well, the 1/2's easy, because that just brings out a 9, right? But expected value of that. Remember how we broke it up? Cosine A, cosine B, minus sine A, minus sine B? What was that equal to?
0.
Expected value is 0, right? Do you remember this from before? So it's really 9. Do you have that down? I don't know.
Yeah, it's not over 2.
18 over 2 is 9. He messed up here. He did what I did. Basically, he used sigma squared. He didn't get the actual value of y squared. He used sigma of y squared, the variance. He didn't actually do that, so it was a mistake. But is it corrected in there or not?
It's not.
Can you correct it? Okay, so that's that part. What's the next part?
Find the autocorrelation function.
All right, this one's tricky. I'm going to just mention this before I'm done. Now, you can see how if it's an autocorrelation function, I'm going to have to take this and multiply it by y cosine omega naught quantity t plus tau plus that, right? Now you get a cosine, and you're gonna have y squared. So the expected value of y squared we can pull out in front. We know that is 18. Then you got the expected value of these two cosine waveforms. And it's a little tricky, there's an identity for this. But it's basically something where it's a pain, it's a huge, in the solutions he has this long spiel of a thing. I'm not gonna ask you to do something that difficult to calculate. The real thing to take away from this is when you're doing this, whenever you're seeing stuff that is either a cosine of omega t plus theta or a cosine squared of omega t plus theta, think identities where you can get down to either a constant, the 1/2 plus something, or break it into something where you can see cosine A, cosine B, minus sine A, minus sine, or plus sine A, plus sine B. If you don't do that, you'll never be able to come up with an answer that makes sense to you, and you can get really fouled up. I'm out of time. I'm gonna do some PowerPoints next time, but here's 6.33 is a very good problem. 6-3.3 for a lot of reasons. I don't have time for it today. I'm gonna give you, anybody do this homework? Weren't there some of these problems I put up? Did you do them? I'm gonna ask you to make sure you do these problems. I'm gonna give you a few others and some reading. But next class period, I'm gonna finish up on a correlation with some specific examples for finite pulses. Pulses of much shorter duration that have non-return to zero, and how the autocorrelation would change. And I'm hoping to get into spectral energy density, or I'm sorry, cross correlation, which you're going to find very easy to understand, and then spectral energy density for a lot of reasons. But that's really one of the big takeaways from this course. All right, thank you for being here. At least the first part makes sense. It'll drive you nuts with some of these trends or some of these